Hi, my name is Lula Wang, and I'm a 10th grader from Greenwich High School. My research project this year was on the lipid-based co-delivery of doxorubicin and siRNA PDL1 as a multifunctional chemoimmunotherapy selective to pancreatic cancer via its MUC1 overexpression. I became interested in this topic because pancreatic cancer is the second leading cause of death worldwide, with a 5-year survival rate of less than 10%. Pancreatic ductal adenocarcinoma, or PDAC, constitutes 90% of pancreatic cancers, which was therefore the focus of my project. One of the biggest challenges in treating PDAC is poor drug delivery efficiency. Current chemotherapy drugs like doxorubicin or DOX trigger apoptosis by blocking an enzyme cancer cells need to divide. However, only 30 to 50% end up reaching the tumor, meaning that a large portion of the drug remains in circulation, causing toxic side effects and increasing costs. To solve this, I developed a multifunctional nanoparticle system, which I named DOX siRNA dope, that improves drug targeting, enhances immune response, and reduces systemic toxicity. Unlike traditional chemotherapy, when I took an HPLC analysis of the original drug sample, my nanoparticle system was concluded to increase drug delivery efficiency to 95%, an almost 100% increase in accuracy from traditional forms of treatment. My research is significant because it introduces a targeted cancer treatment that directly addresses the limitations of conventional chemotherapy. My nanoparticle system works in 3 key ways. Firstly, it selectively targets pancreatic cancer cells using MUC1 antibodies, ensuring that healthy cells remain unharmed. Secondly, it integrates an immunotherapy component to restore immune function, which helps the body fight cancer more effectively and prevents tumor recurrence. And finally, the nanoparticles get taken in through endocytosis, releasing doxorubicin for destruction of the tumor. This research is socially relevant because pancreatic cancer treatments are both highly toxic and extremely expensive. Current treatments require high dosages of chemotherapy, which cause side effects such as irreversible nerve damage, heart failure, life-threatening infections from immune suppression, and even secondary cancers like leukemia, caused by DNA mutations in healthy cells. This led me to develop the novel engineered therapeutic fabricated with multiple coatings that both serve as a chemotherapy and remove immune suppression in pancreatic cancer. To begin, I confirmed successful coating using ATR-FTIR spectroscopy for the nanoparticle flow core, or MPEG-BHAP, the DOX chemotherapy agent, the SiO2 layer, the chitosan layer to allow for binding of siRNA PDL1, and finally, the dope lipid layer, which takes advantage of the tumor microenvironment's aggressive desire to release the nanoparticles with anti-MUC1 attachment. This attachment was proven by the reduction of an alkylamine and the formation of an amine bond. I also used SEMs and DLS particle sizing to demonstrate the continual nanoparticle growth after each additional layer. To test each layer, I designed multiple simulations and studies for each separate component. I first tested the targeting of my novel nanoparticle-based therapeutic, or DOX siRNA dope, through a reconfigured ELISA assay using ATR-FTIR instead of a plate reader. Unlike a standard ELISA application, I designed a system to identify the proper binding and specificity of the nanoparticles to MUC1, which is a glycoprotein overexpressed on only PDAC cells and not on healthy cells. Therefore, I broke apart the well plate and took a spectrum of the bottom piece, which displayed the addition of each reagent, including the completed DOX siRNA dope nanoparticles successfully bound to the MUC1 on the well plate after multiple washes. Next, I had to confirm the proper dissolution of the dope lipid layer once bound to MUC1 to allow for the releasement of the DOX siRNA nanoparticles to be free-flowing and rebind to PDL1. I did this through a pH dissolution study and a time dissolution study, where I took out 10 microliters of a solution with the pH of the tumor microenvironment around 6.8 in comparison to the extracellular fluid with a pH of around 7.4. At 0.1 pH increments, I placed the solution on top ATR-FTIR and I let it dry. I then plotted the peak areas, which determined 100% dissolution at a pH of 6.8, and similarly 100% dissolution at 5 minutes, confirming the timely release of the siRNA nanoparticles, which are then taken in through endocytosis. Now that I have confirmed proper targeting and release, one of the main components of my dual functioning system was siRNA PDL1, which I discovered from previous literature can bind to PDL1. Therefore, it would be practical to add siRNA PDL1 to my nanoparticle so that after binding to the tumor site, it can be released and rebound to PDL1, blocking it from silencing the immune response. Here's an animation I made to more clearly display how the siRNA PDL1 component of the nanoparticle functions. Under normal conditions, T cells properly would detect and destroy cancer cells. However, in pancreatic cancer, the PD-1 receptor on T cells incorrectly binds to the PD-L1 receptor on PDAC cells, suppressing their ability to function and allowing the tumor to evade immune attack. What siRNA PDL1 does is it binds to PD-L1, preventing T cells from incorrectly binding and therefore restoring their ability to recognize and attack cancer cells. This project evolved significantly from its initial concept. Initially, I planned to create a standard nanoparticle drug carrier, but through research, I realized that a simple carrier could not solve the immune suppression problem in PDAC. To improve my design, I made modifications and finally tested my nanoparticles on artificial cancer cells versus artificial healthy cells and took images with fluorescence microscopy. The results confirmed that the undisturbed healthy cells' membranes remained the same throughout 2 minutes. However, the membranes of the artificial cancer cells were disturbed at 60 seconds, and at 120 seconds, they were intermixed entirely. To summarize, I refined my therapeutic into a highly efficient tumor-targeting and immune-activating anti-tumor treatment through multiple design iterations and experimental validation. First, the anti-MUC1 antibodies on the nanoparticle surface were proven to bind to MUC1. Then, the doped lipid layer degrades in the acidic tumor microenvironment and has 100% dissolution within 5 minutes to release the siRNA nanoparticles. These free-flowing siRNA nanoparticles then rebind to the PDL1 on the tumor site. Once bound, the nanoparticle is taken in through endocytosis, releasing doxorubicin, triggering apoptosis, and therefore leading to tumor destruction. While this system was mainly designed for pancreatic cancer, it has the potential to be applied to many other types of cancers by modifying the targeting mechanism. In the future, I plan to expand my research by incorporating specific glycoproteins for different cancers, such as breast cancer and lung cancer, making the approach widely applicable and cost-effective across multiple types of malignancies. I aim to develop a solution that is effective, but also practical, affordable, and accessible worldwide. Expanding this research means improving treatment for millions of patients and contributing to the global advancement of cancer treatment. Thank you for the opportunity to present my work, and I am excited to continue contributing to the future of therapeutic delivery systems and cancer research.